So we're going to wrap up chapter 5 with this video where we'll talk a little bit about calorimetry, heat capacity, specific heat, and start to see some of the calculations that go along with it. So these are two different types of calorimeters. So the calorimeter is the instrument we would use to conduct calorimetry, and essentially by being able to measure temperature changes inside of an insulated vessel, we'd be able to determine heat flow and calculate the Q value, and then if it were for a reaction, also calculate the value for enthalpy change. So the setup on the left is called a bomb calorimeter, and that's because there's a sealed container inside of another sealed container. So things are fully insulated. Typically, this is connected to a computer, and you're getting all sorts of readings. So for industrial applications, like before you're about to scale up the production of a material or a pharmaceutical, you would do a lot of calorimetry measurements on your reactions to just make sure you understand the ways in which heat builds up during the course of a process so you can control it, especially when you scale it up to do it with a much larger amount. The setup on the right is our simple coffee cup calorimeter, and that's pretty much the standard fare that we use in undergraduate chemistry labs to do some basic calorimetry. So we're just really going to talk about heat flow taking place between water inside the calorimeter and in an object that we drop into the water. But in theory, we could also conduct some simple reactions in this coffee cup calorimeter, as long as it's not something that would damage the styrofoam cup. So typically a reaction where we're using water as the liquid, as the solvent, then that would be something totally acceptable to do inside of the styrofoam cup. Measuring the temperature before and after a process and having a little bit more additional information would be all you need to do to conduct some basic calorimetry. So we want to define the terms heat capacity and specific heat. These two terms are different, but we're mostly interested in talking about specific heat, which also gets called specific heat capacity. So when we talk about heat capacity, that's a more general term. And heat capacity is just the amount of energy required to raise the temperature of a substance by 1 Celsius degree or 1 Kelvin. Notice that's interchangeable, right? A change of 1 Kelvin is the same as a change of 1 Celsius degree. So the important thing is heat capacity only talks about substance. It doesn't say a specific amount, but specific heat talks about for 1 gram. So that's a more valuable number to have access to because it relates it also to the amount that we have. So what you see in the table down below here are a bunch of different substances and their specific heat values. So let's highlight a couple here. Here's nitrogen, the primary component of air here. And it says that it costs 1 joule to heat 1 gram of nitrogen by 1 Kelvin or 1 Celsius degree. Then we have something like iron, where it takes 0.45 joules to heat up 1 gram of iron by 1 degree. Metals are easier to heat up than a lot of things, and we can see even easier to heat up than air, but substantially easier to heat up compared to water. So water has this relatively high specific heat. That should make sense, right? You need to input a whole lot of energy into liquid water to get it to its boiling point. That's because it has a relatively high specific heat capacity, whereas when we look at a metal like iron, it costs substantially less to heat it up. That would make sense, right? If I had left a cup of water in my car all day and it was hot, it would warm up a little bit, but if I had the metal seat belt in the sun all day, then it would heat up substantially more. So specific heat is what we're interested in because it relates the energy input to a temperature change for a fixed amount. So if we write that as a more clear-cut expression for specific heat, that'll start to get us more to what we're interested in talking about. So usually we just call it specific heat, but technically it's often written as specific heat capacity. And like I said, we're raising the temperature of 1 gram of substance by 1 Kelvin, again, interchangeable with 1 Celsius degree. So then, if we define specific heat by an equation, it's the heat transferred divided by the mass divided by the temperature change. So now we can map all these things, right? So S will represent my specific heat. The heat transferred, we'll use Q, just like heat flow, temperature change, delta T, and then mass, M. And we're going to use M as a mass in grams. So it's not SI like with kilograms like you saw for some things earlier. It's still going to be a mass in grams when we talk about it. So now we have a relationship between the specific heat, the amount of heat transferred, the mass, and the temperature change. And this should make sense, right? We're saying for a given amount of heat flow Q to a given amount of mass M, what temperature change do we observe? And that's the value that we're going to relate to S. Because this is telling me that if heat flow has a substantial, has a big impact on the temperature, then the specific heat's going to have a low value. But if heat flow has a small impact on the temperature, then it's going to be a relatively large value. So qualitatively, the larger the specific heat, kind of the more difficult it is to raise the temperature of the object. The smaller the value is for specific heat, then the easier it's going to be to change the temperature of the object. So more often, I guess I can write this here before we go on, more often we see this equation written as not as a fraction, but as Q equals ms delta T, or, and I don't think this is as common anymore, but you'd have C for specific heat capacity, or even C subscript S, so mcs delta T. Those are all writing the same equation. So we'll start by thinking about two types of problems that I can solve. One problem type I could solve would be where we are told the specific heat of a substance and then the question is going to say, how much energy do I need to change the temperature of a given amount of the substance by a given temperature? So this is our example problem, right? If you're on the PowerPoint, then you're kind of popping through this. If you're just looking at the PDF, it's kind of all here. But here's all the information, right? I'm told the specific heat of water. That's a known constant for water. We'll see water a lot in these. I'm told the mass of water that I have, and I'm told the temperature change that I want to undergo. And the question is saying, how many joules? So I'm being asked to solve for Q, which is here. And this is kind of, like I said, the typical way we see that equation written. So I've got everything I need, right? The mass is given, the specific heat is given, and the temperature change is given. So again, notice here, right? This says Kelvin, this says Celsius degree. That doesn't matter, right? A change of 20 Celsius degrees is the same as a change of 20 Kelvin. I should probably match the units when I actually calculate it out, but they're going to cancel anyway, so it should all work out. So then Q equals ms delta T. All those values have 3 significant figures, so when I solve for it, I got 2090. So it says I need 2090 joules of energy if I'm going to heat up 25 grams of water from 5 degrees Celsius to 25 degrees Celsius, or more generally, to heat it up by 20 Celsius degrees as liquid water. Okay, so pretty straightforward there. I have one for you to figure out as well. So per usual, right, we haven't had a practice problem in a little while, but you can pause it here and work it out on your own, or just kind of keep going along with me. All right, so let's see what's happening here. It tells me the specific heat of my liquid is 2.42 joules per gram per Kelvin. How many joules are needed? So that's my question again, like last time. How many joules are needed to raise the temperature of 55 grams of this ethylene glycol from 10 degrees Celsius to 45 degrees Celsius? So this is going to look a lot like what we just did, right? It's basically the same problem with new numbers. So here's our equation, Q equals ms delta T. And all this stuff is given, right? M is 55 grams. S is 2.42. And this time I'm going to write it as joules per gram per Celsius degree. Same difference, right? And then delta T, final minus initial, so that should be 32.5 Celsius degrees. Very minor point, right? Degrees Celsius means I'm telling you about a temperature. Celsius degrees meaning I'm telling you about a change in temperature in Celsius degrees. Okay, so we're good to go here, it looks like, right? Q equals 55.0 grams times 2.42 joules per gram per Celsius degree times 32.5 Celsius degrees. So I made my units match up this time. It doesn't change the approach compared to the last time we did it, but now the grams in the numerator go with these grams in the denominator. Celsius degrees here goes with Celsius degrees, and then we get our answer. Everything has 3 significant figures and we're multiplying, so we'll keep 3 significant figures. So 55.0 times 2.42 times 32.5. I got 4325.75. 3 significant figures would make this 2 my cutoff number, and it's followed by 5 and more stuff, so I'm going to round up. 4,325.75 will round to 4,330 joules. 3 significant figures to match the 3 significant figures I have with my values there. Okay, so in the example, it was set up to solve for Q. Then in this one we just worked out, it was set up to solve for Q. But it could also be set up to solve for delta T or S or even M, depending on exactly what we're looking at in the problem. So let's see one example of that. Okay, in this question it says it requires 886 joules to heat 22.4 grams of an unknown liquid from 18 degrees Celsius to 24.6 degrees Celsius. And then what are they asking us? What is the specific heat value of this liquid? So now, rather than Q equals ms delta T, we're solving for S, so S equals Q divided by M divided by delta T. Same as before, I think we have what we need, right? Q is 886 joules. That's the energy it requires. M is 22.4 grams. And delta T, final minus initial, 24.60 minus 18.00. That's 6.60 Celsius degrees. So I've got what I need here, right? S equals Q over M delta T. Q is 886 joules. M is 22.4 grams. And delta T is 6.60 Celsius degrees. Again, and I kind of end up doing this by default a lot, 3 total significant figures for all the values, so that's what we'll report with. So I got 5.9929, etc. But our cutoff number for 3 total digits would be this second 9. It's followed by something smaller than 5, So it's just going to round off to 5.99 joules per gram per Celsius degree. That's our specific heat value. That's a pretty large specific heat value, right? It's larger than the value for water, so it's telling me that it's even more difficult to change the temperature of whatever this unknown liquid is compared to water. Okay, so that's a good introduction into the Q equals ms delta T equation. We're going to see one more application of it, but kind of following along the same way. So what I was telling you earlier is this coffee cup assembly could be suitable for doing certain chemical reactions. If we were using like water as the liquid, as the solvent, then that would be totally appropriate. So it says if we were carrying out a reaction in aqueous solution in this simple calorimeter, we could indirectly measure the heat change for the system by measuring the heat change for the water in the calorimeter. So what ends up being true if we're in a calorimeter, and again, I know I say this all the time, but this is something we'll talk a lot more about in the second semester class. In a calorimeter, the heat flow and the enthalpy change are opposites of each other. Normally, they're the same, but the reason for that is there's no heat flow in either direction when we're looking at a coffee cup calorimeter. Heat is not flowing in from the surroundings. Heat is not flowing out of the system to the surroundings. So normally an exothermic process would release heat that would escape. But if I have an exothermic process in a calorimeter, the heat that normally would get released is going to stick around and heat up the contents inside. So all of a sudden things are going to get flipped around, because if Q equals ms delta T, but now I'm in an insulated vessel, delta T is going to change in the opposite way I normally would expect. So a positive Q and means a negative delta H, which means exothermic. A negative delta Q means a positive delta H, which means endothermic. And all that would only apply if we were conducting chemical reactions inside of the calorimeter. That's not what we're interested in right now, but like I said, it's something that comes up in the second semester class. Okay, so then what can we do here to have a interesting problem to look at in our calorimeter? Well, we'll rely on the same fundamental concepts that we would for figuring out the calorimetry, the enthalpy change for a reaction. We'd use water as our solvent, knowing its specific heat, and then we can measure heat flow easily with Q equals ms delta T, since we know our value of S. So that's how it would work for a chemical reaction. What we're going to talk about instead is I'm going to drop a piece of metal of known mass into the coffee cup calorimeter with water of known mass and known temperature, and use that information to figure out the specific heat of the metal. So that's my goal in all this that we're looking at on this page, is ultimately I want to figure out, based on the behavior of the metal in my calorimeter, what is its specific heat value. So building off the same ideas we just talked about, but a little more to do in this case. Okay, so in this one, I worked out kind of the first half of the problem, and then we'll solve the second half after we've done that. Okay, so let's dissect our information here. 22.5 gram piece of an unknown metal heated to 100 degrees Celsius, so that's its initial its mass and initial temperature, then dropped into a coffee cup calorimeter containing 50 grams of water at 25 degrees Celsius. So we know its mass and its initial temperature, and then it tells me the new temperature of the water. So the most important thing to know about is that metal is in the water. So this 28.5 degrees, that represents the final temperature of the metal, as well as the final temperature of the water. These two things are in contact with each other, so they've reached what we call thermal equilibrium. Okay, all that being said, what am I being asked in this first part that's already solved? How much heat flowed into the water? So we're back to what we saw earlier, right? Just Q equals ms delta T. Make sure you're using the right values here, right? Mass of water, it tells me in the problem, is 50 grams. This is our constant for water. Just use 4.18. 3 total digits is fine. And it went from 25.0 to 28.5. Remember, this always means final minus initial, so delta T will be 3.5. So we got all of that. We plug it in. 3.5 only has 2 significant figures, so my answer only ends up with 2 significant figures. Remember, that 0 doesn't count unless I put a dot, but it tells me 730 joules of heat flowed into the water from the metal when I dropped the hot piece of metal in. So then in the next part, it says, how much heat must have flowed from the metal to the water? Well, this is an important thing to think about as well, right? The only cause of the water receiving 730 joules of energy was the hot piece of metal that was dropped in. So what that means is the heat that flowed out of the metal is equal and opposite to the heat that flowed into the water, right? This is the bookkeeping that we're able to do to say whatever came in had to come from somewhere, so the metal must have given us that heat. So that means the Q for the metal is negative 730 joules. And then finally it asks me, determine the specific heat of the unknown metal. Well, if Q equals ms delta T, we already came to the conclusion we can rewrite that as S equals Q over M delta T. But now I have all of those values to plug in. So it'll be Q, which is now negative 730 joules because it's Q metal. And now instead of mass of the water, we'll plug in mass of the metal, which is 22.5 grams. Well, then what about delta T of the metal? Well, the final temperature is 28.5, but the initial temperature, it tells me for the metal, was 100.0. So that's Q over M delta T. The delta T will be negative, right, because it went down to 28.5 from 100. So let's see what we get here. And we should only report it to 2 significant figures, I guess. So it'll be 0.4537, so just 0.45 would be 2 significant figures. You're right, 0.4537, then the 5 is our cutoff number since 730 only has 2 significant figures, so then my answer will just be 0.45 joules per gram per Celsius degree. So that's kind of the most complicated thing we're going to be looking at from the perspective of calorimetry now. The reaction stuff, like I said, will come later, but that's something that we're able to do for now. So there's a lab experiment. I think it's for me, the 4th lab experiment that I call experiment 3, where we'll talk about this sort of thing where you're dropping a metal into the calorimeter to figure out its specific heat. So that was kind of the main math problems that we want to look at once we introduce Q equals ms delta T. I think I have a couple more points to bring up, and that's really it for this section. So remember I told you that if we were in a fancy lab, like making pharmaceuticals or making some new materials, and we had to scale up some reaction processes, then we'd collect data on a bomb calorimeter like this. And so this fully insulated vessel connected to a computer collects all sorts of data that lets us figure out everything that we want to know. Technically, though, in this bomb calorimeter, it's a sealed vessel. That means that there is some pressure buildup, so it's not officially heat flow at constant pressure, but as long as a ton of pressure doesn't build up, then we can say whatever values we measure in the bomb calorimeter, they're pretty close to the expected enthalpy change. And here I just pointed out, not such a huge thing, but the volume in the bomb calorimeter is constant. What that means is I'm really measuring delta E, not delta H, but that typically doesn't matter. So this is more or less the setup that you would expect at an advanced lab for figuring out heat flow before you, like I said, scaled up a reaction. Okay, that's really it for the stuff that I wanted to talk about here. These last 4 or 5 slides are just kind of extra information, nothing I'm going to ask you about. Since we're talking about energy, you might know about this 4-4-9 rule for carbs, fat, and protein, right? In terms of fuel value, carbs and protein give you 4 kilocalories per gram, whereas fat is 9 kilocalories per gram. That's really how they determine calorie values for things, by understanding the amount of carbs, fat, and protein, and using the 4-4-9 rule for that. Lots of diets are based on counting your carbs and fat and protein by using this 4-4-9 rule. Yeah, nothing too much else interesting on this one, but just some energy values that we can think about. Energy in terms of fuel, we're looking at kind of fuel efficiency in terms of kilojoules per gram. So something like burning wood, pretty inefficient in terms of the energy we'll actually get out of it. Things like oil and gas and natural gas, all pretty similar to each other in terms of energy per gram. Since it's in energy per gram, hydrogen gas, H2, has a really low value because you're not using up that much mass in order to generate a good amount of energy. Hydrogen is a fuel source. I think it's still around. It's not caught on like some people might have hoped it would, but it still works and it still has interest because it's a small amount of energy or a large amount of energy per gram. And also burning hydrogen does not generate carbon dioxide, so that makes it particularly appealing as a fuel source. We'll see how it goes, but I think there are lots of challenges to using hydrogen as a widespread fuel source, and we can see other technologies are certainly passing it up in some ways, but we'll see. The only other thing, and remember I told you I'm just collecting data that I thought was interesting that you might want to see, but not something I'm going to ask you about in a test. Just from government websites, I found the energy by source and sector over the last 10 years and collected a few of those data points. So just kind of seeing how things are going in general over time, it might be interesting. So on the left side, right, it says 36% of energy source was petroleum, 26% natural gas, and in 2011, 20% was coal and 9% was renewable, 8% was nuclear. The usage on the right side doesn't change that much. We're still pretty much using energies in the same way we were before. Then if we jump to 2017, you can see that natural gas increases considerably and coal drops off considerably. So some of the pickup is in natural gas, some of it is in renewable energy. Nuclear stays pretty much the same, but coal usage went down a whole lot from 2011 to 2017. The breakdown of usage, again, pretty similar. And then I just got the 2020 data. I guess it's available now. And now what you see is, again, well, let's see, the natural gas goes up again, renewable energy goes up a little bit again, and coal goes down again. Nuclear, it's still pretty stable in the way things are going. So interesting stuff, I think, that we're seeing a boom in natural gas. I think in Texas we know that is clearly the case. Same with renewable energy. We're seeing more windmills and solar power, but clearly in the last 10 years, it's coal that's being replaced, right? Almost half the coal that we were using 10 years ago is not being used and now replaced with renewable energy and natural gas primarily. Okay, last slide here. They just use the general term renewable energy, so I was curious to know what are they talking about? How does it really break down? And it breaks down, I would say, more or less like we would probably expect it to. Wind and biofuels making up the most of it. Solar, not as much. Hydroelectric, not as much as wind. But those are the kinds of things we're seeing as our usage. And these are national numbers, not world numbers. So it's talking about how renewable energy is showing up in the US as of 2020. So I think that's pretty exciting stuff, right? That renewable energy is picking up, and natural gas totally better than coal. So that's in terms of pollutants and efficiency. So those are great things to see. And renewable energy growing is definitely good for all of us. So like I said, just kind of most of these books talk about energy at the end of their energy chapter, but not something I'm going to ask you about in a test or anything like that. So hopefully you feel comfortable after this video working with Q equals ms delta t, trying to figure out how to set it up and what you're solving for in each case. That's really the focus there, and then understanding what's going on in a calorimeter, particularly the fact that heat flow and enthalpy are not the same in a calorimeter because it's an insulated vessel. So yeah, I'll go ahead and stop there.